By this point in our math journey, most of us have been told that all of the interior angles of a triangle here, all three of these angles are going to add together to equal 180 degrees. Okay? So this is pretty common knowledge to us. But what about other shapes that are not triangles? We can find the measurement of any polygon's internal angles. The only thing is that they don't all equal 180 degrees. Only a triangle does. You guys may have learned at some point, maybe in passing, maybe it was like a big deal, that the internal angles of a square, because a square by definition has 4 90-degree angles, this is going to equal 360 degrees. But in all honesty, we can just also look at it as a square is made up of two triangles. Two triangles, each at 180 degrees, is also going to equal 360 degrees. Okay? And honestly, we can do this with any shape. Okay? We have a pentagon here, and we have a shape that has 11 sides that I don't quite know the name of. But if we come down here and we make triangles out of all these shapes, we split them into as many triangles as we can create, each triangle equaling an internal angle measurement of 180 degrees, then a pentagon is going to have an internal angle measurement. All of these angles are going to add together to be 540 degrees. And in this case, with this 11-sided shape, we can create a whole bunch of these triangles, connecting this vertex with all of the opposing ones. Just like so. That's going to give us 9 triangles. If each triangle is 180 degrees, and so on and so forth, then 9 triangles times 180 is going to give us 1,620 degrees. All of our internal angles here are going to add together to be 1,620 degrees. Now, you guys may have noticed here with 3 sides, we have one triangle. Obviously, one triangle is made up of 3 sides. Here with our 4 sides, that's 2 triangles. With our 5 sides, that's 3 triangles. And with our 11 sides, that's 9 triangles. Okay, there is a formula for this. You can find the internal angle measurements of any polygon without having to draw out the triangles like we have here. And you guys may have noticed a pattern. For our 3 sides, we only have 1 triangle. Okay, this is 2 less than the number of sides. Here it's 2 triangles for 4 sides, so 2 less than the number of sides, so on and so forth. So if each triangle is 180 degrees, and we multiply that by however many triangles we have, and the amount of triangles that we have is 2 less than the number of sides, our n equals the number of sides, okay? Then we have ourselves a formula here. This is the measurement of internal angles. Okay, we can do that for any shape here. Okay, if you have an octagon, so an octagon has 8 sides. So we can use this formula then. If it's 180 degrees, because we're taking that 180 degree measurement for each triangle that we have, and the amount of triangles that we have is 2 less than the number of sides, we can say, okay, 180 times 6, because this is going to come out to be 6, is going to be 1,080 degrees. So in total, all of those are going to equal 1080 degrees. Okay, but if we want to figure out each individual measurement for each angle, let's draw ourselves a hexagon here. So a hexagon is going to have 6 sides, okay? And we plug in our little formula. So 180 degrees for each triangle multiplied by 2 less than the number of sides. That's going to give us an internal angle measurement of 720 degrees. Okay? So we know that all of these angles are going to add up to equal 720. Now pretend that this is a nicely drawn perfect hexagon. All of these angles are going to be congruent. They're all going to have the same angle measurement. So for a perfect hexagon, we can take the total angle measurement, so the internal angle measurement, and we can just divide that by the number of angles. Okay, so here we're going to have 6 angles, because this is a hexagon. A hexagon has 6 sides, 6 angles. So we can take this 720, so 720 is our total internal angle measurement, divided by 6, which is going to give us a measurement of 120 degrees per angle. Okay, per angle. All right. That is how we can find the individual measurements of any perfect polygon. Okay, the total angle measurements using this formula, and then just sort of reversing the process in a way to find each individual angle measurement. Okay, now outside of the internal angles, let's draw ourselves a hexagon again. Or a pentagon, I guess. This is going to be a pentagon. So, along with our internal angles, we've also talked about our external angles. Let me just draw some dotted lines here. Remember, our external angles are angles that are supplementary to our internal angles. Okay? And let's make a note of that over here. External angles are supplementary, which means that they're going to add together to be 180 degrees. Okay? So whatever these two angles are, they're going to equal 180, so on and so forth. Now, again, if this is a perfect hexagon, which means that all of these angle measurements are going to be congruent, then we can use our formula here. So we got 180 times 2 less than the number of sides we have for each of our triangles. That's going to give us, again, like we decided earlier, 540 degrees. Okay? Which means that all of our individual angles are going to equal 108 degrees. Okay? So this is 108 degrees. This is 108. This is 108, so on, so forth. Okay, so then for our supplementary angles, each of the ones that are supplementary to this one are then going to equal 72 degrees. Okay, because 108 plus 72 is going to give us 180. So all of these are going to be 72 degrees. Okay? If we add up the sum of these external angles, we're going to notice something. We have 72, 72, 72. That's going to give us a measurement of 360 degrees. Okay? You can think of it as another way of thinking about it is that with each corner that we take, we turn at the degree of this angle. And eventually, if we keep turning for each angle, we're going to go around in a circle. And as a lot of us know, the measurement of a circle is 360 degrees. So any polygon, we can draw another hexagon here. Another hexagon here. We decided already that each of these internal angles of the hexagon is going to equal 120 degrees, which means that each of these external angles are going to equal 60 degrees. Now, if we take 60 and we multiply that by the amount of external angles that we're going to have total, 6, that is also going to give us 360 degrees. So we can use this information to find any of the amount of external angles here. Because if we are given any polygon, we can find the amount of internal angles. We can find then the measurement of each individual angle, or we can just say, okay, well, if all polygons are going to have an external angle measurement of 360 degrees, then we can just divide it by the number of angles in the shape. Okay, the number of angles in the shape. We can find each individual one. Okay? So this information can help you if you have any missing variables. Everything is going to be equal to 360. If you are trying to find the internal angle measurement and it gives you variables, or if it gives you some unknown numbers, that information also can be used to find any information regarding these angles. Just by remembering, let's write out the formula one more time. For the measurement of interior angles, okay? Remember, the formula is 180 degrees, because that's the internal angle measurement of a triangle. And we can find out how many triangles are in a polygon by taking 2 less than the number of sides. And remember that n here represents the number of sides in a polygon. Okay? And the measurement of the external angles is 360 degrees. Always, always, always. So you can use this 360 degrees divided by the number of sides or the number of angles. It's going to be the same regardless of the shape, is going to give you the individual external angle measurements. Okay? That is how we can use this information to find the measurement of any polygons.